My name is Neha. I'm a PhD student at MIT, and I'm going to talk about how we can handle conflicting operations in database transaction processing. And this is joint work with Cody Cutler and Robert Morris at MIT and Eddie Kohler at Harvard. So we've already seen this afternoon, applications which use databases are composed of transactions. Here are 3 transactions. They're examples. They're not super important. And maybe they're used in a social networking site. Transactions are composed of operations on records, and those operations might be as simple as reads and writes or gets and puts. And the database needs to ensure that the transactions happen atomically and serializably. Let's focus on the first transaction. So this is pretty simple. It's just incrementing a value for a key. An application might need to run millions of this transaction, for example, to update counters. Main memory multicore databases are very good at scaling transaction workloads when writes don't contend. Unfortunately, application data access is almost always skewed, and applications actually do experience write contention on popular data. So here's a fun example of that. You might remember this selfie. It became the most retweeted and favorited Twitter post of all time, and it was so popular that it broke Twitter. Now, in an application with transactions, maintaining counters like this would use something like that increment transaction I just showed you, and those transactions would all contend on the same 2 counters. So the performance, and in particular the scalability, of this one type of transaction actually matters quite a bit. So that's actually a problem because existing concurrency control enforces serial execution of transactions when they operate on the same record. So here we have 3 cores, and each core is executing an instance of that increment transaction on the same record, X. What happens here is they need to happen one at a time. We can't actually take advantage of the fact that we have multiple cores. In optimistic concurrency control, this happens in the form of aborts and restarts, and in 2-phase locking, it's blocking on locks. So this is a big problem because it means that with conventional concurrency control, as we see here, we can't take advantage of more cores to get higher throughput. Performance flattens out. So in the rest of this talk, I'm going to show you how our system, Doppel, actually scales on contentious transactional workloads. So one interesting thing to note here is that if you're only doing increments on a record, you actually can perform these transactions correctly in parallel by using a trick called Percore variables. So here we have 3 increment transactions, and they're all happening on the same record, but they're actually incrementing Percore variables. We say that these are Percore slices of X, and we say that X is split across the cores. So this is actually a really common technique for individual variables and concurrent algorithms, but it's not used in transaction processing systems. So can we do this correctly? Well, yes, if we're only doing increments to X, increment commutes, and so it doesn't really matter what order these increments happen in on the different cores, we're going to get the same answer no matter what. So that's great for our increment transaction, but unfortunately we want to support many other types of transactions in a database. So these transactions might also be running concurrently with the increment transaction, and they might be running on the same keys. Both of these transactions need to do their reads and writes atomically. Also, transactions can have arbitrary code in them. We have an if statement here, and we might need to return values to the caller that reflect exactly how that transaction was ordered. So it's unclear how to run these 2 transactions correctly while using split data. And that's the challenge that we're trying to address. We want to do fast, general-purpose, serializable transaction execution with per-core slices for contended records. We introduce a new technique to solve this challenge called phase reconciliation. So the idea behind phase reconciliation is that the database automatically detects contention on a record in order to split it among the cores. Once this happens, the database starts cycling through phases. We call them the split, reconciliation, and joined phases. In the split phase, writes to contended records are done per core. We then reconcile these writes so that in the joined phase, we can execute any combination of operations in any transaction using concurrency control. We've implemented this technique in Doppel, which is an in-memory key-value transactional database. So the contribution of this work is a phase reconciliation technique, and in particular, defining a set of splittable operations that transactions can use to execute on split data. We do efficient detection and response to contention on individual records. We also do reordering of split transactions and reads to reduce conflict. And finally, we do fast reconciliation on split values. So for the rest of this talk, I'm going to describe phase reconciliation and exactly how it works. I'm going to give you a few more details about operations and what it means when I say an operation can be split. I'm going to tell you how our database, Doppel, detects contention, and finally we'll do a performance evaluation to see if this even works. Okay, so let's start with the split phase. The split phase transforms operations on contended records, in this case X, into operations on Percore slices. So here we have 4 cores, they're executing 4 different transactions, and each transaction, some of the transactions are writing to different keys. So transactions can operate on both split and non-split records. X is split, but Y and Z are not. We use optimistic concurrency control to ensure serialization to the non-split records. So you see here that on core 1, that transaction's writing Y, and the transaction on core 3 is also writing Y. So we need concurrency control to ensure serialization for these transactions. Split records have an assigned operation for a given split phase. So in this split phase, the assigned operation to X is increment. And so we can do all the increments that we want on X in this split phase. But let's say we see a get. Some transaction wants to read X. Well, this is kind of incompatible with what we're doing so far. We can't actually process a read of X given the state that X is in. Its value is split across all the cores. So what we do is we stash this get, and we initiate a reconciliation. And so what that means is that all threads hear that they should reconcile their Percore values. They stop processing Percore writes, and then they add their local values to the global state for X. It's important to note here that reconciliation only happens for keys that have been split, and there's only one reconciliation per split key per core. So reconciliation is actually quite fast. Eventually, all of these, the reconciliation will finish, and then we're able to go back and resume the stash transaction that wanted to read X. And this happens at the beginning of the next phase, the joined phase. Once we enter the joined phase, we can process new transactions using optimistic concurrency control. So in this phase, we have no notion of split data, which means that we can do arbitrary operations. Now, this actually turns out to be a very useful way to organize our transactions, because we can batch the work of many transactions across phases and reduce conflicts. So we actually execute many split transactions in the split phase, and we accumulate these stash transactions to execute later. This amortizes the costs of reconciliation over all of the split transactions. We enter the join phase, and then we execute all of those stash transactions. And what's interesting to note here is that these get operations would have conflicted with the increments in the previous phase, but they actually don't conflict with each other here at all, so they can be done in parallel. So here's a summary of phase reconciliation. We hope that many contentious writes happen in parallel in the split phases, and reads and any other incompatible operations happen correctly in the joined phases. So now let's find out what makes an operation splittable. So here's the operation model we use for Doppel, and here's the API. Developers write transactions as stored procedures, which are composed of operations on keys and values. So the first two operations should look pretty familiar. They're get and put, the traditional key value store operations. The next three are operations which happen on numeric values. So we already saw increment. So what happens here is that this operation applies an increment of n to k's value. The next two operations are special. We introduce them, and one is an ordered put, and the other is an insert to an ordered list. You can find out more about these operations in our paper. Only some operations are amenable to splitting. The top two key value operations are actually not, but the rest are. And so let's look a bit more closely at what makes an operation splittable. So we're going to use max as an example. So we talked before about how commutativity of these operations is important for correctness when we're executing on Percore slices. Well, we also need to be able to efficiently reconcile these values. So here we're executing max operations on the same record, X, but on Percore values, X is split. And notice that we're only keeping one piece of state per core for x. And that piece of state that we're keeping is the current value for x given the operations that that core has seen. So for core 0, it's 55, because that's the max value that it's seen so far. We don't, for example, keep logs of operations, and this means that we can reconcile per core values in time order the number of cores. And the reason that we can do this and get the correct result is because max commutes with itself. These are all commutative operations, and so the answer that we get is compatible with any ordering of the max operations. So that's great. We can correctly reconcile x at the end and figure out what x should be. So this gives us some intuition about what kinds of things we can split and what we can't. So here are the properties of operations that Doppel needs in order to split them. First of all, they need to be commutative. Second, they need to be able to be efficiently reconciled. They need to be on a single key, and they shouldn't have a return value. So the first property is for correctness, and the second is for performance. The last two are actually limitations of our system for simplicity. They're not strictly necessary. The single key restriction doesn't affect functionality, since applications can compose many operations together into a transaction. However, another limitation of our system is we only allow one type of operation per record per split phase. So if x is split and is seeing increment operations, then you can't apply any other type of operation to x, even if it's commutative, until the next split phase. Now I'll give you a little bit of insight as to how we detect contention. So Doppel counts the number of times that a conflicting operation on a record causes a transaction to abort, and it uses this count to consider whether or not to split that record among the cores. Similarly, if a split record is causing a lot of transactions to be stashed in the split phase, then Doppel considers moving that record back to not being split. So it's very dynamic, and as workloads change and different records contend, Doppel can adjust to the changing workloads. So now let's look at a performance evaluation to see how phase reconciliation works. Here's the experimental setup and implementation. We run all experiments on an 80-core Intel server. Doppel's implemented as a multi-threaded Go server, and we run one worker thread per core. Transactions are procedures written in Go. All data fits in memory, and we don't measure RPC in these experiments. And all of the following graphs are going to measure throughput, so higher is better. Okay, so here are the questions we want to answer in this performance evaluation. First of all, how much does Doppel improve throughput on contentious write-heavy workloads? Second, what kinds of read-write workloads can benefit? And third, does Doppel improve throughput for a realistic application that might have many different kinds of operations and transactions? And we're going to use Rubus and Auction Benchmark to answer that. So let's get to the first question. So this graph demonstrates one of the most extreme cases where phase reconciliation can help. This is a workload of increment transactions where every single transaction is incrementing the same key. And we're running this on 20 cores. So what we see here is that Doppel gets much better performance than optimistic concurrency control or two-phase locking because it's able to execute the conflicting writes in parallel, leveraging the 20 cores. OCC and 2PL can't, and they have to execute the transactions serially. So Doppel gets roughly 20 times the performance of 2PL in this case. Now we'd like to answer the question of how much conflict regular concurrency control can tolerate before we start to need something like phase reconciliation. So this graph shows throughput varying the percentage of transactions that write to that one hotkey. So previously, all transactions were writing to that one hotkey. Here, at the far left, all keys are being accessed uniformly, and there's a million of them. And on the right, every transaction is incrementing the same hotkey. So that's the same point as in the previous graph. So what this graph shows is that even with small amounts of contention, anything past 5%, the throughput of conventional concurrency control drops significantly on 20 cores. After only 5% writes to the contended key, phase reconciliation actually becomes very helpful. Okay, so that was 20 cores. Now let's take a look at how well Doppel scales as we increase the number of cores. So in this graph, we're varying the number of cores on the x-axis, going up to 80, and we're measuring throughput. So this is again an example of the most extreme case where every transaction is incrementing the same key. So what we see here is that Doppel gets almost linear scalability, while, as might be expected, OCC performance collapses with increased cores. At a high number of cores, the communication we use for phase changing starts to become a bottleneck. Now we'd like to evaluate Doppel's performance on a mixed read-write workload. So we're going to introduce a slightly more complex workload called the like benchmark. So this benchmark is supposed to simulate users liking pages on a social network. So there's two tables here. There's a users table and there's a pages table. And there's two transactions. One's a read-only transaction, which reads how many likes a page has and the user's last like. And then the other transaction increments a page count of likes and inserts a user like for a page. In this benchmark, we have 1 million users, 1 million pages, and we have a Zipfian distribution of page popularity. So some pages, like Barack Obama's, are going to be way more popular than other pages. Now, the thing to note here is that both reads and writes are going to be more towards the popular data. And so Doppel is going to end up splitting the page like counts for popular pages. But that means that those counts are also going to be read more often, and hence they're subject to being stashed. So this graph shows the throughput for both Doppel and OCC on a workload of 50% reads and 50% writes. So even though many of the read transactions are getting stashed, Doppel still gets better throughput than OCC because it actually benefits from batching the Percore writes on the few contended pages together in the split phase, and then doing the reads without conflict in the joined phase. And so let's investigate that a little bit further. So here we're looking at the same workload, but we're varying the percentage of read transactions on the x-axis. So at the left, all transactions are users liking pages, and Doppel performs much better than OCC because likes of popular pages are happening in parallel, and there's no contention. At the right, all transactions are reading, and Doppel and OCC both get very high throughput because there's no conflict. As we move to the right, increasing the percentage of reads in the workload, more and more transactions that are reading popular pages are getting stashed, and they have to wait until they can execute in the joined phase. Eventually, Doppel decides that it's no longer worth it to mark popular pages as split. And after this point in time, it stops marking any data as split, and so all transactions happen using optimistic concurrency control. The key point here is that Doppel's batching technique actually helps up to a pretty high percentage of reads, and after that point, we get comparable throughput to regular concurrency control. So now let's see how well this technique applies to a more complex application. So we're going to use Rubus for this. So Rubus is an auction benchmark. It's modeled after eBay. There are users, and they bid on auctions, they write comments, they list new items, and they do a lot of searching and viewing of items for sale. There are 1 million users and 33,000 auctions, 7 tables and 17 transactions. And in the Rubus bidding mix, as it's defined, 85% of the transactions are actually read-only. So the Rubus bidding mix doesn't define any skew in the workload, so that means that there's a uniform distribution of all accesses. That means that all auctions have the same level of popularity, and you're as likely to bid on one auction as the other. We introduce a slightly new workload with a skewed distribution of bids. And so what that means is that a few auctions are much more popular than other auctions, and so they're more likely to get more bids. So here's the most interesting transaction in that workload, and we've rewritten it to work with Doppel's operations. What's really nice is that it does work very well with Doppel's operations. So the top 3 lines are updating auction metadata. We're updating the number of bids for an auction. We're possibly changing the max bidder and how much that is. And in a skewed workload, these are the operations that are most likely to be quite contended because they're updating auction metadata. So the popular auction, which is getting a lot of bids, is going to end up having a lot of these rights. Now, the nice thing about this is that all of these operations are actually commutative, and so they could be split, and they can run in parallel, even if users are bidding on the same items. The last line is a put, where we're actually writing the bid to a table, and it's not commutative, but most likely this is not going to conflict because we're generating a new key every time, so each bid is going to have a new key. Okay, so here's the performance of the Rubus bidding benchmark on 2 different workloads. On the left is a uniform workload, and on the right is a skewed workload. So we see in the uniform workload that Doppel performs slightly worse than OCC due to the overhead of phases and tracking conflicts. However, once we look at the skewed workload, we see that OCC's throughput drops significantly. And what's really interesting here is that this contention is only caused by 8% of the transactions. So only 8% of the total workload is operating on potentially contended data, the popular auctions, and yet OCC's throughput drops a lot. Doppel is able to get 3 times the throughput of OCC just by moving these contended records over to be split data and performing these operations in parallel. So what's the key takeaway here is that our technique, phase reconciliation, has comparable performance with no contention and actually helps throughput significantly when there is contention. So there's a lot of related work in this area that inspired us. There's commutativity in distributed systems and commutative concurrency control. We also use the optimistic concurrency control algorithm in Silo. And we were very much inspired by the idea of split counters for scalable multi-core OSs. So in conclusion, Doppel can achieve parallel performance when many transactions conflict by combining Percore data and concurrency control, and performs comparably to OCC on uniform or read-heavy workloads, while improving performance significantly on skewed workloads. And so here's a website if you'd like to learn more, and hopefully the code will be coming soon, and I'm happy to take questions.
Hi, Charlie Johnson from HP Labs. About 30 years ago, there was a thing that was popular called escrow transactions, which is very similar, except not sliced. But one thing you could do with escrow transactions is you could calculate up the commits and aborts and keep the bank branch balance from going below 0 or above some, or the inventory level, so you wouldn't sell more books than were printed, which maybe Amazon is the only one who can get away with that. So do you have some way of handling that with slices or some idea of how to do that?
So that's a great question, and escrow transactions are definitely part of our related work. So there's 2 things I want to say about that. First of all, my understanding of escrow transactions is that they don't use the Percore slices. And so even though they are able to do these commutative operations and avoid aborts, they end up contending on that data, which is really bad in a multi-core setting. But I think that I talked about properties of commutative operations, and I think state-based commutativity would be really interesting here, and that's actually the next thing that I want to look into.
Hi, Brad Karp, UCL. Really enjoyed your talk. I had a question about ordered put, and I know you said that that's in the paper, but then you used it in a transaction, and I think I might know what it does.
Okay.
So it looks like it's useful for sorting bids by the amount bidded, for example.
Yeah.
Okay, so that sounds like that could be a useful optimization for a system other than your system also, just like avoid having to read a value and then write it back. So is this just a general purpose, useful optimization for key value stores, or is there something about your system particularly that made you really want to implement this?
That's a good question. I think that ordered put is actually pretty similar to something like the last writer wins policy when you have like a timestamp or something like that. So in that sense, it is very useful in distributed systems. We haven't really evaluated its use in a lot of different contexts. But
Thanks.
Hi, Henry Ching from Stanford University. I noticed that you give us a lot of throughput numbers, but you don't talk at all about latency.
Yeah.
Is there a particular reason for that? I mean, we expect it would be a little bit slower, but I'm curious as to how much.
Sure. So there are latency numbers in the paper. I didn't have a lot of time to include that. Basically, latency is proportional to phase length. So you have to end up holding transactions until a phase is passed so that you can actually apply those transactions in the join phase.
Is there an upper bound on the phase length?
Yeah, we actually set our phase length to about 20 milliseconds. I have a graph on that that's probably going to be very confusing, but basically that up and to the right sort of indicates that average read latency is proportional to the length of the phase.
Thank you.
On that note, let's thank Neha one last time.